I started as a mathematician. So I did my bachelor's in mathematics, pure mathematics, and then I transitioned slowly to physics. So I would say my background has been always between mathematics and physics. So I'm a theoretical physicist currently. So I've always worked in mathematics and physics combined. Um, but right now, my research is mainly focused in quantum gravity. That's the topic I have done starting from my PhD up until now, and specifically loop quantum gravity and spin foam approaches. So that's the research I've done. But recently, I'm also interested in more application of computational methods, mathematics, to physics problems. So I position myself as theoretical physicist interested in computations, like techniques and then approaches, how we can apply them to some physics problems. We know about quantum theory, which works very well at very small scales. And then there's gravity, like you mentioned, which works very well on very large scales. And so the point of quantum gravity, the reason why we need quantum gravity is we need a theory that will be somehow consistent across all scales. So we're trying to put these two theories, quantum theory and gravity, which works on different scales, put it together to form what we call quantum gravity. And that should work on all scales. So it's the name of a theory. I would say it's a name of a theory that is not complete yet, but it already has a name. We know that it should work on all scales. So that's what quantum gravity is useful for. It's a technique. So it's originally founded by Richard Feynman. He's a very famous physicist. And there were other people like Schiller, Dyson, who worked on these formulations too. But in short, it's a technique that is used to compute some quantum properties about particles, fields. It could be anything. So the idea is that let's say I have a particle at point A, and I want to translate this particle to point B. So the path integral approach is to consider all possible ways for this particle to go from this point A to this point B. So there might be, some wiggle ways. It can be a straight line. It could be different ways. So the idea is that if I want to describe, assign some quantum number to this kind of motion, I will sum all possible ways for this path, for this particle to go from point A to point B. And this is kind of the idea of path integral. So it's a quantum property. It's used in quantum field theory, quantum mechanics, quantum gravity also. It's used there. But it's mainly to capture some properties which you would not capture in the classical sense, but it's only in the quantum sense. But it does so by considering all possible paths. So that's why the name path integral. And integral also means sum. So, consider all possible ways from path A to path B, put them all together, and this will describe for you some quantum property of this particle. Gravity is different from a particle in the sense that gravity has to do with the nature of space and time itself. So path integral, I mentioned it doesn't just work for particle. I can describe the motion of a particle from point A to point B. But in terms of gravity, what I would describe would be the geometry or, the nature of space and time at one instance. And then I want to describe the nature of how the nature of space-time would change from between one instance to another instance. So I'll consider all possible ways, space and time will change or will go from this one instance to this other instance. Another simple way you can think of this is when people say gravity, space-time, it's also about geometry. So, I can describe how I can go from a certain geometry to another geometry. And there could be different ways to describe this. So path integral, so it means that path integral is a very general technique that works for particles to gravity itself, space and time, which are not necessarily particles, or fields also, electromagnetism, quantum field theory. Path integral is also used there. So it makes path integral a very universal technique across many fields. And in quantum gravity, it's also very useful. I mean, when you want to study about how the nature of space and time changes between one instance to the other, path integral is the natural way you would ask this question. So path integral is very useful. It allows to ask very neat questions and then answer them in general. So I mentioned path integral is a technique. So there's a formula for it. You write down your formula, and but in gravity or in quantum gravity, you can write this down, but it's only formal. It's not. There are many ingredients that go in which you have to make precise in order to get a good number out of this. So there are many reasons why it's all not done yet. First, because when you write it down, it's only formal. So one thing I should say is, so one property of this path integral, or the formulas, one thing that goes into the formula is some phase factors. So you have some phase factors, and this basically gives you just some oscillations. How if you have it's just like, if you have cosine and sine functions, you have these sine waves, how they oscillate. It's sort of like that. So there's a phase factor in the definition of a path integral, and depending on how fast these oscillations are, it can make your computations very challenging. So you need to have this under control. So I mean, in short, there are many ingredients in the path integral, which I can tell you later, which makes it very difficult to compute. It depends on the situation you are considering or the physical problem you're trying to solve. I mean, you can, in some situations, it's easier than others. I mean, I mentioned particles or electromagnetic fields, or in those situations, it's easier to compute the path integral. But once you bring gravity or geometry, there are so many things you have to consider. And this makes the problem very hard. I mean, should I continue with more things, or I can?
It's up to you.
Okay. So maybe I can mention one of the very challenging things, which is that, because gravity is also about geometry of space-time, and we are summing over geometries, we have to have an understanding of what things we are summing over, right? And this is one of the main problems. Like, how do you quantify the things you are summing over? And how do you determine whether you are counting something more than once, or you want to avoid these things? So they are very little small questions that you have to address in order to make your path integral well defined. And for gravity, it's very challenging. There are so many ingredients that come in and makes the path integral not so easy to tackle. But there are people who are trying so hard to overcome some of these obstacles. One technique people have used in the past was to do something we call the Euclidean path integral. And I mentioned before, like the issue of these oscillations, you have a phase factor, and this is because there's exponential I times some function. So you try to tame these oscillations by going to Euclidean formulation, and what it does is remove this phase factor with some smooth function, and this, changes it. And this was one of the ways you can solve these problems. So going from some Laurentian formulation to Euclidean formulation. There are also other people who say, let's define this rather on a lattice. And this, it's a very, like the path integral is just formal, but if I put it on a lattice, I know exactly what some of the variables are, and I know what I'm summing over and things like that. So I can put it, if I put it on a lattice, I have some finite numbers. I can also put it on a computer and I can solve it. So like I mentioned so if you do the Euclidean, go from oscillations to something very smooth, then, and on top of it, you put it on a lattice, then your problem becomes somehow easier to tackle. And people have done this. So I've mentioned two different ways. Put it, go to Euclidean or put it on a lattice. So that's one way. But if you stick to the exponential imaginary times some action, which is if you stick to very fast oscillating things, there are some other theories which try to also tame these oscillations. And there is this is well known as Picard-Lefschetz method. And the idea of this method is to extend your space, your space of configurations. So I say space of configurations, but it's the space that captures all the possible ways, your paths or the possible paths. So you change this space to some complexified version. So you extend this to a complexified version, and now you have much bigger space to explore. And in this much bigger space, you can somehow deform your integration contour to a path that now the oscillations are low, minimal. So not very much oscillating, but they are somehow damped, just like it will happen in the Euclidean formulation, where you switch from exponential to exponential is to exponential minus Euclidean action. And in doing so, you can also perform computations using these Picard-Lefschetz methods. So go to the complex plane and change your integration contour. And this is also another method people have come up, which is also useful and can help to solve. And people have used this actually in some physical scenarios to study cosmology and other situations, other physical models. So these are just some few methods out there to somehow tackle these problems. Path integral itself, it's a tool, it's a technique. So you can have different theories, and then you can apply these techniques too. So in quantum mechanics or quantum field theory, there are different techniques that people use to tackle problems in quantum field theory, for example. Typically, there is the canonical approach, and then there is the path integral approach. And in some situations, these two methods give you the same answer. So in quantum gravity, path integral is also like a tool. It's an approach. So there are other people who do canonical approaches to quantum gravity, and so path integral is also another approach to tackle similar problems. But I like path integrals because it makes the questions that you can ask in quantum gravity a bit more refined and clean, and then you can understand these questions a little better and try to give problems or like solutions to these problems. That's why the path integral approach I like it. But it's not the only way. There are some other approaches that will also tackle the same problem. And I think even in general, one would expect that, you can always bring these different approaches together. Like if I can describe some situation using path integral and you come up with another method, we should agree on what our solutions are to some extent. So in essence, path integral approach to quantum gravity, it's a technique, it's a tool to allow us to refine some questions and answer them. But there are some other methods people use, and they are also equally useful. So one thing path integral does, which maybe might be useful, is what people call semi-classical results, which is, you are not, it's somewhere in between quantum and classical. So you are not purely classical, and you are also not deep quantum. And the idea is that, you have these paths that you are summing over, but there are some paths that contribute more than other paths. And these paths that contribute more tend to be classical. So those are the ones that maximize or minimize your action in the path integral formulation. And there are paths that are close to this path, this classical path, that would contribute, to the next leading order. So you can use path integral formulation to kind of address what away from classical, what some phenomena would look away from classical physics. And this is actually what has been done in cosmology, for example. There is this famous issue or problem in cosmology about, it's not a problem, but it's a proposal in cosmology about the universe going from nothing to what we have now. And this is a proposal by Hartle and Stephen Hawking. You can use path integral formulation to understand some semi-classical properties of this proposal and see if indeed our universe right now can indeed come from nothing. So you can put it in a path integral formulation and study it, and you will get the results, and you can test with what we see currently and see if this makes sense. So that's one way you can use path integral to address something semi-classical that is close to classical but not quite. So there are many phenomena you can cook up and then try to test this using path integral. And so semi-classical is one of the good things to do. One of the main issues in quantum gravity, even if path integral is just it's a technique, it's a method, and it cuts across many approaches, so it's also easy to understand many different kinds of approaches to quantum gravity. But the issue is that even once you write down your path integral partition function, we typically call partition function, there are many situations where it's challenging to solve this. So in my opinion, we need more techniques, like more computational techniques or analytical methods to actually solve these path integrals. So, and this would, once you're able to solve this, it gives you a better idea of what quantum gravity is in general. So that's one thing. We need better methods to understand this. And one other issue that we face a lot is, what is the interpretation? Especially when it comes to quantum gravity. If I have a path integral from some geometry at one instance to another geometry and I sum over all this, like, what am I computing? What is the interpretation there? Some people have given some thermodynamic interpretation. Some people have given, it gives you an amplitude where you measure some probability from going from this instance, geometry at this instance, to the other instance. There are different interpretations out there. So there is also the interpretation question of what actually the path integral is computing in quantum gravity, because you sum over many things. You can sum over topology, you can sum over geometry, So what is it that you are really computing? Quantum gravity is fun. So there are a lot of challenging problems that you can do in quantum gravity. So I think if you're a student, maybe if you like challenge, it's nice. So there are many problems that can challenge you. My advice would be to study a bit more, so to broaden, the things that you know, because quantum gravity is like I mentioned, it's the name of a theory that doesn't exist yet, and we might need approaches from different parts. So it's good to know a lot about different fields, because like also the name quantum gravity, you have to understand quantum, you have to understand gravity. So you really have to broaden your knowledge in all these aspects. So that would be my advice, that for students who want to get into quantum gravity, it's good to understand the basics of the things you are doing right now, because it will become useful and will give you more clarity and understanding if you tackle problems in quantum gravity, which cuts across many different. And the nice thing is that sometimes you can come up with connections which might be unusual, because coming from different fields, you can come up with connections, and many people appreciate this in quantum gravity. Because sometimes it's good to understand the same problem from different perspectives. So my advice would be broaden your knowledge and learn some mathematics, learn some physics. Philosophy is also good. Just try to understand many things, which I know it's a lot, but I think it's not impossible. I mean, you don't have to know very deep, like everything, but have a good idea of what maybe different topics try to address. Yeah, that would be good.